Okay, so today we'll study electromagnetic waves. Do you guys know what electromagnetic waves are?
Electric current produces a magnetic field.
So waves that have both electric and magnetic fields in them. Okay. Do you know examples of electromagnetic waves?
Light.
Hmm? Light is an electromagnetic wave. Okay. Radio waves are electromagnetic waves. So here's gamma rays. Okay. X-rays. So here's a wave. You've seen water waves. The wave is traveling in this direction, and this wave has both electric fields and magnetic fields. Okay. And in this wave, you can see that the electric field and magnetic field are perpendicular to each other, and that's always true. And they're also perpendicular to the direction of travel. Okay. So here's an electromagnetic wave. This is how an electromagnetic wave looks like. What are examples of electromagnetic waves? So let's see that. Gamma rays are electromagnetic waves, X-rays, UV light, visible light, infrared microwaves, radio waves. They're all electromagnetic waves. Okay. And in vacuum, they all travel at the same speed, 3 times 10 to the power 8 meters per second. Okay. And their speed is denoted by c. Yeah. So they all travel at this speed. Yeah. So this is what we're going to study in this chapter. Okay. So we'll look at their properties, we'll study how they're produced, and so on. Okay. So here's how you produce electromagnetic waves. Now, I don't know, you might remember this from Physics 1, but we talked about gravitational waves. So for instance, you take a mass and you accelerate a mass. All right. So and the easiest way to do it is grab hold of a mass and make it jiggle like that, and it will emit gravitational waves like that. Okay. So if you want to produce electromagnetic waves, you have to do the same thing, except that instead of a mass, what you have to
Sorry, I was saying charges.
exactly. Okay. So you got to take a charged particle, so an electron, for instance, okay, and jiggle it like this back and forth, and you'll emit electromagnetic waves.
And so, like, light works by just the electrons jiggling in it, propagating throughout space.
So yeah, this accelerating charged particle emits electromagnetic waves. Okay. So now the question is, how do you jiggle this electron? So here's how you do it. You learned about an LC circuit in a few chapters ago. All right, here we go. So here's an inductor, and this is essentially acting like a capacitor. This is a dipole antenna, okay? And the frequency at which this thing oscillates, if you guys check out one of your previous slides, its frequency of oscillation is 1/root of LC, okay? So what this is, okay, so here's LC, this, here's this, and here's the resistor. So you have an oscillating circuit, an AC source, okay? And this thing, you'll have a source whose frequency matches this, and you'll set up an AC current. This is coupled via this inductor, and here's a dipole antenna, okay? So in this antenna, you have a AC current flowing, okay, and that's essentially jiggling an electron, okay. So this thing will get positively charged, negatively charged, and half a cycle later, this will be negatively charged and this will be positively charged, okay. So essentially this is like jiggling an electron, and you emit electromagnetic waves. All right, so this is how an FM radio works. So for instance, all those FM stations, they emit using a dipole antenna, and the frequency of this source is what? For what is the frequency of these FM signals? About 100 megahertz. Okay. So that's the frequency at which this oscillates. Okay. So do you guys understand? So again, to send out an electromagnetic waves, you just have to jiggle an electron. Yep. So if you want to send out gravitational waves, you accelerate a mass, and if you want to send out electromagnetic waves, you accelerate a charge. Okay. And you guys remember, so to emit detectable gravitational waves, you have to jiggle a very massive object, like a black hole. And the way to jiggle how do you jiggle a mass? Huh?
Like moving it?
I'm sorry?
Like moving it?
Yeah, how do you move it?
External force.
Yeah, so for instance, that's what the sun does. The sun is making the earth go around, which is essentially two harmonic motions. But the earth, it's too small a mass, that'll send out very weak gravitational waves. For us to be able to detect them, what you have to do is you have to jiggle a black hole. And essentially two massive black holes will go around each other, and they will emit gravitational waves. Okay? All right, but today we are going to produce electromagnetic waves. Okay, so we are going to make it a charge oscillate and send down electromagnetic waves. All right, so that's what's happening in the background, but let's look at the mathematics of it. Okay. So electromagnetic waves were predicted by Mr. Maxwell before they were detected, okay, before we realized what they were. Okay. So let's look at this. So electromagnetic waves is what we are studying. Here are the Maxwell's equations. Okay. So these equations were known before we knew about electromagnetic waves, or before we understood the nature of electromagnetic waves. Okay. And so we'll be concentrating on this equation and this part of that, the last equation. Okay. So what this equation is telling you is time-varying magnetic fields produce electric fields. Okay. And then in one of the chapters we saw that electric currents produce magnetic fields. But in this chapter what we'll see is that time-varying electric fields also produce magnetic fields. Okay. So that's what we'll be using. All right. So for instance, the way you see this is you can see this. So for instance, let's say you have a battery and a long wire, and then it's charging a capacitor. Okay. So as the current is flowing in this thing, the charge on the capacitor is increasing and the electric field is increasing. Okay. And this current, as you know from one of the previous chapters, will produce a magnetic field like that. Okay. And this time-varying electric field, as the charge on the capacitor is increasing, the electric field is increasing. this term will be exactly equal to that term. Okay? So that'll produce a magnetic field just like that. Okay? So time-varying electric fields also produce magnetic fields. All right, so as the electric field is increasing in this direction, the magnetic field produced will be like that. Okay? All right, so now let's show you how Maxwell came to the conclusion that electromagnetic waves exist. Okay? So we'll do a little Calc 3. Okay? By the way, so what this is telling you is, okay, so you saw that charges produce electric fields and moving charges produce magnetic fields. And the Lorentz force law just tells you to detect electric fields, you need charges, and to detect magnetic fields, you need moving charges. Okay? So the Lorentz force law gives you the force on a charge in the presence of an electric field and the force on a moving charge in the presence of a magnetic field. Okay? All right. So we saw that. So this equation tells you time-varying magnetic fields produce electric fields. Okay? And this is a differential form of the equation. And here is the integral form of the equation. Okay, so what this is saying is, this is also showing you the configuration. So if you have a magnetic field that's increasing in this direction, the electric field will be concentric circles like that. Okay? And what this equation is telling you is the line integral of the electric field around a closed curve is equal to minus rate of change of magnetic flux through that enclosed curve. Okay, that's what this equation is telling you. Anyway, so if the magnetic field is changing, this will be the configuration of the electric field. If the magnetic field is increasing in this direction, coming out of the plane of the paper. What will happen to the electric field when the magnetic field is constant? If the magnetic field is not changing with time. That's right. So if magnetic field is not changing with time, this term will be 0. The magnetic rate of change of magnetic flux will be 0. This term will be 0. And this will have to be 0. Okay? So time-varying magnetic fields produce this electric field. Okay? So that's this equation. Okay? Now let's see this equation. Okay? An example for this equation. Okay, so in that equation, this equation, so here is a capacitor that is being charged, and as a capacitor as more and more charge flow into the capacitor, this electric field is increasing, and when this electric field increases, as the electric field is increasing, it's inducing a magnetic field like that. Okay, and that's what this guy is saying. So the line integral of the magnetic field is equal to mu naught E naught epsilon naught d, the rate of change of electric flux. Okay. So as the electric flux is increasing in this direction, the magnetic field is produced like that. If the electric field stops changing with time, this magnetic field will go to 0. Okay. So the magnetic field is produced as long as the electric field changes with time. And notice, if the magnetic field is increasing like that, the electric field is in the opposite direction. Okay. Electric field increasing like this, the magnetic field is like that. Okay. So these are the Maxwell's equations. Maxwell's, using 4 equations shown, predicted the existence of electromagnetic waves. So Mr. Maxwell predicted the existence of electromagnetic waves using these equations. Okay, that propagate through vacuum with the speed of light. Okay, once he predicted it, then we went looking for them, and then eventually we realized that light was an electromagnetic wave and so on. Okay. All right, so what he said was, let's study these equations in vacuum. Okay. In vacuum, this term is 0. There's no charge density. This term is 0. Okay. So the four equations become, in vacuum, you're studying divergence E equal to 0, divergence B equal to 0, curl of E equal to minus del B by del T, and curl of B equal to epsilon naught mu naught del E by del T. Okay. All right. I don't know if you've done this yet, but you might do this in your calculus classes. Okay. All right. So what this is saying is, A is a vector field. You guys done it?
We just started this, yeah, we just started this today.
Okay. So, well, perfect timing. All right, A is a vector field. What does that mean? That at every space-time location, okay, if you want, we'll do that. Yeah. So at every space-time location, you're associating a vector. Okay. So if you take the curl of this vector field, what that's equal to is gradient of the divergence minus del square A. Okay. This del square operator is the following. Okay. So that's the del square operator. Okay. And this is in the Cartesian coordinates, in spherical polar coordinates, it'll have a different form. Okay. All right, so this is an identity. Curl of a vector is a gradient of divergence of the vector minus del square A. Okay, so if we do that, we'll apply that to the electric field. So this is an electric field in vacuum. That's what we are considering, remember? Okay, so now curl of A in vacuum is minus del B by del T. Okay. So curl of this will be, you have a minus del B by del T, and then there's another curl, so we'll take a curl. Okay. But curl of B in vacuum is equal to that. Okay. So we'll substitute that. So there's the minus epsilon naught mu naught del by del T times del by, so there's a del by del T, and you had another del by del T. So you get del square E by del T square. All right, but this guy from this identity is gradient of the divergence of E minus del square E. In vacuum, this guy is 0. This guy is 0. So that guy was 0. So what you have is minus del square E equal to minus 1 over C squared del square E by del T squared. Okay. So Mr. Maxwell arrived at this equation one afternoon. Okay. Now you can do the exact same thing for the magnetic field. So we'll start off with, we'll do curl of B, okay? And curl of B, remember, well, let's look at this. Curl of B is minus epsilon naught mu naught del E by del T. So curl of B is, and okay, so epsilon naught mu naught, Mr. Maxwell called it 1 over C squared. And you'll see in a second why this is called that. Okay, so there is epsilon naught mu naught is 1 over C squared. Okay. So we'll come to that in a bit. Okay. So curl of B was 1 over C squared del E by del T, and curl, so there's the other curl. Okay. but curl of B is related to del B by del T, and so and curl of E is minus del B by del T. Okay, so I'm going to substitute that minus del B by del T. And this is del square B by del T square. That's what that is. 1 over C square, and the minus is there. But this fellow from the identity is gradient of divergence B. This guy is 0. So that's equal to minus del square B equal to that. So one afternoon, Mr. Maxwell realized that in vacuum, both electric and magnetic fields satisfy the same differential equation. Okay. Now, of course, you can try and solve this equation. Whenever you have a hard equation, what do? You try and solve it for the simplest case. Okay. So now what we're going to do is we're going to consider the following case. So you have both E and B satisfying this differential equation. So in general, E is zt and B is a function of x, y, z, and t. Okay, so what Mr. Maxwell did is try the simple case. Let's consider the case where E is a function of only x and t. Okay, and B is a function of x and t. Okay. So what does that mean? Let's see, how does this look? Okay. So for instance, how this looks is the following. Okay. So here is x, and as time evolves, this will change. So this electric field, the electric field at any location depends only on the x coordinate. It does not depend on y and z. That means in this entire plane, the electric field has the same value. As x changes, its value will change, and you can see that here at this value of x, there is the electric field, and at this value of x, there is the electric field. So as x changes, the electric field value is changing. But its value is the same in the YZ plane. So in that entire plane, it's the same. Similarly, for the magnetic field, it's changing with x, but in the YZ field, it's the same. Okay, so these are called plane waves. And what it is so here's a plane. In this plane, the electric and magnetic fields have the same value. But as you move along the x direction, the value changes. Okay. So that's what we're considering. Okay, so we'll consider this simple case. Okay. So now let's substitute that in this equation. Del square E equal to 1 over C square del square by del T square. Okay. And we're considering the case where E is only a function of x and t. All right, what is del square? It's del square by del x square plus del square by del y square plus del square by del z square. E x t equal to 1 over c square. All right, but E is only a function of x and t. So these will drop off. These terms will, do you guys understand? These terms will give you 0. Okay. So now you have del x square E x t All right, you guys are differential equation experts, partial differential equation experts, and you can easily find solutions to this, and a solution to this is the following. And you can test it out. here's a solution to it. Okay, so varying with x and t. Okay, so we'll say E naught j hat cosine kx minus omega t. Okay, where k is called the wave number. K is the wave number. See, E is varying only with x and t, and omega is the angular frequency. Okay, and and this fella, this C, is related to k and omega, and C equal to omega over k. Okay, k is equal to 2 pi over lambda, and omega is 2 pi f. So what I'm saying is I just pull this out of my head. This guy solves this differential equation. Okay, you can substitute that. E naught is the amplitude, what is J? J is the unit vector along the y-axis. Okay, so here's a solution. Okay, so the solution to this differential equation is that guy. And that guy is just exactly this guy. So you see, here is a sine or a cosine function along the y-axis, and as time increases, which way is this wave traveling? This wave travels to the right. See, as time increases, x has to increase to keep this phase constant. Okay, so this is a wave traveling to the right. Okay? And that's what this guy is describing. Okay, so here's a plane wave. This is known as a plane wave. Why is it called a plane wave? Because on this plane, in the yz plane for a given x, E is constant. E and B are constant. Okay? So that's why it's called a plane wave. So here's a wave traveling to the right. Okay, and so it turns out that electric and magnetic fields are always perpendicular to each other. So the solution to the identical equation for the magnetic field, so del square B by del T square, del square by del X square B X T 1 over C square del square. Okay, so since B and X are perpendicular to each other, it's B naught cosine kx minus omega t k. Okay, so you see that if the electric field is pointing along the y-axis, the magnetic field will be along the z-axis, and that's what that solution is. Okay. And again, they're traveling the wave speed. This is the wave speed, and that's equal to omega over k. Yep. So there's a plane wave, electromagnetic wave that's traveling to the right. Okay. And Mr. Maxwell discovered this solution. Okay. So one afternoon, having coffee at a coffee house, this is the solution Mr. Maxwell discovered. Okay. And you see, they all travel at this speed. Okay. And that happened to be the speed of light that they had measured. So that afternoon is when they realized that light was an electromagnetic wave. They didn't know before then that light was an electromagnetic wave. All right. So you guys see the power of mathematics? Using these equations, he realized that the electric and magnetic fields will satisfy this differential equation, partial differential equation. The solutions to this differential equation is these guys, waves that travel at that speed. Okay. So that was a pretty happy afternoon for Mr. Maxwell. Okay. So once he realized that all electromagnetic waves travel at the same speed of light, that electromagnetic waves exist. So again, here's the equations again for a plane wave. Once the existence of electromagnetic waves are predicted, what would you do? So your mathematics predicted the existence of electromagnetic waves. What would you want to do? You want to go experimentally verify it. Okay? Do they exist? And here's Mr. Hertz. Hertz verified them. Okay? So here's the deal. Okay. So this produces electromagnetic waves, and there's the dipole that will emit electromagnetic waves. And here's a tuning circuit. Okay, so in modern parlance, so here could be the FM radio station that's emitting FM waves, and this is your radio that's picking up the waves. Okay, so now, I mean, wireless communication is part of your life, so those waves are carrying energy which get transferred to the circuit. The circuit picks it up, and you parse that signal. All right, so here's what Mr. Hertz did. Okay, so this equipment is described by this this circuit. So here's a AC source, okay, and this you generate a frequency equal to the square 1 over omega LC for this circuit, which is coupled via this inductor to the spark gap. So this is acting like a capacitor. Okay, and so here essentially, as this capacitor is switching back and forth between positive and negative, as this thing is oscillating, it's like jiggling that electron, okay, which is emitting this electromagnetic wave. So the electromagnetic waves are emitted, and this tuning circuit picks it up. So Mr. Hertz demonstrated all waves carry energy. So there must have been electromagnetic waves which are carrying energy to have sparks develop there. Okay. All right, so I've said a lot, so let me review it again. Okay. So what did Mr. Maxwell do one afternoon? So here's an identity. Okay, he applied this identity to these four Maxwell's equations. And then he realized that electric and magnetic fields in vacuum must satisfy this equation. Okay, so now if you consider the simplest case where these guys depend on only in x and y, so for the simplest case, electric fields and magnetic fields must satisfy this differential equation. The solution to this is that, and these are propagating waves. So his equation predicted the existence of propagating electromagnetic waves. Okay. And Mr. Hertz verified their existence. Yeah. So here's how the electromagnetic waves look like, and here was the experimental verification by Mr. Hertz. Yeah. And that's why the units in which frequencies are measured are called hertz. Okay. And hertz is 1/2. All right. So again, in a plane electromagnetic wave, the electric and magnetic fields satisfy this partial differential equation. Again, what is this partial differential equation telling you? See, this is a pretty neat equation. This is relating the spatial derivative of the electric field to the time derivative of the electric field. Okay? And look at this dimensionally. So this is electric field divided by distance square. C is a velocity, C times T is a distance. C squared times T squared is distance squared. Okay. All right, so you have to notice all of that. Yeah. So again, there's the partial differential equation. Again, the neat thing about this is second spatial derivative is being related to second time derivative. Okay. So both electric and magnetic field satisfy this differential equation. This is called a wave equation, and you will study this you'll come across this in many situations. Okay. So we solved it in the simplest case. So again, here is the general equation. You want to remember this. Okay, so this is the wave velocity, okay, del square by del t square. Okay, we solved it in the simplest case where it's not a function of y and z. Okay, so that's the wave equation. All right, now we'll study some properties of this electromagnetic wave. Okay, so again, you already see that the electric and magnetic field are perpendicular to the direction of travel. Okay. All electromagnetic waves have this property. Gamma rays, X-rays, UV light, infrared light, visible light, okay, radio waves, they all have this property. All right, so here's a plane wave. Here's the amplitude of the wave. Here's the amplitude of the electric field, amplitude of the magnetic field. K is called the wave number, and it's related to the wavelength of the light. What is the wavelength? Crest to crest distance, that's the wavelength. Okay, so you see, so there's the wavelength. If you want to measure it using the magnetic field, here's the wavelength. Okay, and that's the wavelength. Frequency is how many times? Frequency is, what does F stand for? What does F stand for? Yeah, so for instance, if you stand there, how many wavelengths will pass you in 1 second? It also stands for, so here's the electric field pointing now, half a cycle later it'll be pointing down, and then it'll be pointing back up. That is one oscillation. How many times will it oscillate per second? That's the frequency. Okay? And so for instance, for your FM radio, it's about 100 million hertz. And that's what that means. The electric field is oscillating 100 million times a second. Yep. So that electron is being jiggled 100 million times a second. Yep. Your cell phones, do you guys know what frequency your cell phones work at? About 5 gigahertz. Okay, so that electron is being jiggled 5 billion times a second to produce that wave, the signal that carries this, that your cell phone infrastructure uses. Okay. All right, so K is the wave number. It's 2 pi divided by lambda. Omega is the angular frequency, 2 pi times f. And the speed of the wave is frequency times the wavelength, which is omega divided by k. Yeah. Again, this was the apparatus that Mr. Hertz used. This is producing the electromagnetic waves. So the electromagnetic waves are emitted by this capacitor, and this is the detector, the tuning circuit. So this is this radio station, this is your radio. That's picking up the signal. Okay. Now here are some properties of plane electromagnetic waves. Okay, and again, why are they called plane? Because in this plane, in the YZ plane, their value is the same. the value changes only with x. Okay. So you can be at any location on the electromagnetic wave, and the ratio of the electric field to the magnetic field is always C. Okay. So this is giving you the relative strengths of them anywhere on the wave. So if you measure the electric field at this point and the magnetic field at that point, the ratio is equal to C. Okay. So their amplitudes also have the same ratio. E max divided by B max is equal to C. Okay. So at every instant, the ratio of E and B field in an electromagnetic wave is constant and equal to the speed of light. And this is in vacuum. Yeah. Both E and B satisfy the wave equation. What was the wave equation? Partial, the second spatial derivative was equal to 1 over C times the time derivative. Okay, so here is the wave equation. So both E and B satisfy the wave equation. So electromagnetic waves travel in vacuum at 3 times 10 to the 8 meters per second. Yeah. What is the speed of gamma rays in vacuum?
3 times 10 to the 8.
Very good. What is the speed of infrared?
3 times 10 to the 8.
Oh, exactly. All right. All electromagnetic waves travel at that speed. Yeah.
Same with gravitational waves and everything else.
Right. Gravitational waves travel at, yeah. And that is the limit. Nothing can travel faster than the speed of light, and all signals choose to travel at that speed. Yeah, interestingly. So, and we're talking all in vacuum. The ratio in an electromagnetic wave at any location, the ratio of the electric field to magnetic field is equal to that. They obey the principle of superposition. What does that mean? What that means is, let's say you shine multiple beams of light. This beam produces an electric field like that. Beam 1. Beam 2 produces an electric field like this. So the net electric field is just the vector sum of these two guys. Okay? That'll be the electric field. And it doesn't matter. You can have as many beams as you want, and the electric field at that point will just be the sum of all the electric fields. Okay, that's what that means. That also means that, so if you have so you have seen, we have drawn this quite a few times. Let's say for one beam, the electric field comes like that. And for a second beam, the electric field reaches this point, this location, with a negative amplitude. What will you see there? I'm sorry? Nothing. The two electromagnetic waves will cancel each other. Okay? And that's what was used in gravitational wave detection. Okay? So one light beam came with an electric field, was positive there, and the second beam came with an electric field of negative there, and they cancel each other. Okay, so here are some numbers for an electromagnetic wave. So here's the electric field, here's the magnetic field. C is the direction of propagation. Okay, so here's a radio wave, a typical radio wave. FM radio has a frequency about 3 times this, 2.5, 3 times this. Okay. So for a frequency of 40 megahertz, the wavelength is 7.5 meters. For this radio wave, the wavelength is roughly half the width of this room. Okay. The amplitude of the electric field is 750 Newton per coulomb, or 750 volts per meter. Okay. So that electric field, so how do you detect this electric field? You stick out an antenna, and this electric field will drive a current in this antenna. Okay. And then you can pick up this guy. This antenna acts like a, okay, so this antenna acts like a capacitor, and you can pick up this signal, feed it to an inductor. Okay. Okay, so this signal is picked up by this antenna. You feed it to an inductor, and then the inductor talks to another. It's part of a transformer, and this is so this is your tuning circuit. Okay, so this guy. So here's how radios work. Here's how wireless. Here's an electromagnetic signal that's inducing a current here. That signal is transformed to this circuit via transformer, and here's the processing unit. Okay, so here's the electromagnetic wave, and in your cell phone there's the tuner that's picking up the signal, and then this guy processes the signal. Okay. How was this guy produced?
Jiggle.
I'm sorry?
Jiggle.
Jiggle. So this guy was produced like so. Yeah. So that guy was produced like so. Okay. So you see the production and processing are similar devices. Okay. And at the heart of all wireless receiving devices is this tuning circuit. Okay. Where this guy is acting as a capacitor and this guy is your inductor. Okay, so the maximum value of the electric field is that, and B max, amplitude of the magnetic field, is this divided by that. See, the amplitude of the magnetic field is about 1/100 the magnetic field of Earth's magnetic field. Okay? So on the cell phone signal that you're receiving, the magnetic field is roughly that. Yeah. All waves carry energy. How do you know that waves carry energy? How can you, okay, here's the water, here's the surface of a lake, okay, and I set up a water wave by dropping a rock in the water. How can you prove that this guy carries energy?
It moves something on the surface of the water.
That's right. So if you have a boat floating, when the wave goes by, it moves it up and down. You go stand outside in sunshine, you feel the warmth. So the waves are carrying you energy, and when you absorb the waves, energy is transferred to you. Okay. So electromagnetic waves also carry energy. Okay. This fellow is called the pointing vector. What the pointing vector tells you is the following: how much energy is passing per unit area per second. Okay. So energy passing per unit area per second is the pointing vector. Okay, so this is also called the intensity of the beam. Okay, and the pointing vector is given by 1/mu0 E cross B. Okay. So power is energy per second. Power per unit area, the intensity is given by the pointing vector. Okay. Now, of course, these guys are changing with time, and they're changing very fast with time, so we'll want an average pointing vector, the average energy passing, and you'll see in a little bit the average energy or the average intensity is 1/2mu0 E max B max. Okay. All right. So the intensity is the average intensity, and that's equal to E max B max by 2mu0. Okay. Now, so here's a beam of light. Okay, so here are the, fix this. Here's a beam of light. Okay, so what you can think of this as the energy density, how much energy is contained per unit volume, and how much will pass times the speed of light. Okay, so in 1 second, if you're standing at this point, the amount of energy that passes you is the energy density times the speed of light. That's the intensity, okay? And you can think of the energy contained in this unit volume, you can express it in terms of the electric field or the magnetic field. You guys remember that anytime you create electric or magnetic fields, there's energy in those fields, okay? And since these two guys are related, the energy per unit volume can be expressed in terms of either the electric field or the magnetic field, okay? Again, remember, anytime you create electric and magnetic fields, you've created energy, or you've stored energy in the electric and magnetic fields, okay? So the intensity of the light is the energy density times the speed of light. Energy density is the energy per unit volume. That energy per unit volume can be expressed in terms of the electric field or the magnetic fields, okay? So that's what this is. So the energy density in terms of the electric field, and there's the energy density in terms of the magnetic field. And okay, so the intensity of the electromagnetic wave equals the energy density times c, the speed of light. Energy density times the speed of light. Yeah. Now, okay, back 200 years ago, we used to think that light was a wave. Okay? In 1905, Einstein said light is actually a bunch of photons, and a whole bunch of photons, when you have a stream of photons, they behave like a wave. Okay? So when you shine a beam of light, it's like you're shooting a stream of bullets. Okay. Now, if you shoot a stream of bullets to a dummy, momentum is transferred to the dummy. The dummy flies, right? Okay. Well, can you do that with light? If the light is a stream of photons.
It just takes a lot more. That's like sun sails.
Right. So you can do that, and this thing demonstrates this.
Well, it's like, you know, if you shine a really powerful flashlight in someone's eyes, like, they're going to get blinded because of all the photons hit.
Yeah, but you're not, that's the energy being deposited that's burning you, okay?
Yes.
Yeah, yeah. But here we want to demonstrate momentum transfer, okay? And this device does that. So okay, so here's how you understand this. What is the momentum of a particle moving with velocity v? M times v, right? Okay, the kinetic energy of a particle is, what is the formula for the kinetic energy?
V squared.
Half mv squared. Okay, so you see momentum is sort of energy divided by v. Okay, do you guys understand? If you divide this by v, you get mv. Okay, so the momentum of a photon is defined as, and again, the energy of the photon is given by h times the frequency. This is what Einstein showed us. So the momentum of the photon is its energy divided by c. All right, so that's, so right now we'll ignore them, okay? And this is a low energy equation. Okay. All right, so you see the momentum is of a photon is that. Okay, so there's the energy of the photon, HF, and there's the momentum. So if you have a bunch of light and that's the total energy, the momentum carried by that beam of light. So if you have, let's say you have a beam of light that big and its energy content is U, its momentum is given by its energy content divided by C. Okay, so now if this beam of light gets absorbed by a dark surface, that's how much momentum is transferred to this. It's like if you shoot a bullet and the bullet embeds in a dummy. Okay, so here's a bullet, here's a dummy. This had MV, and the bullet embeds in the dummy. What happens? Now the dummy flies with M plus M times V dummy. Did you guys understand that? Momentum is conserved in this collision. Okay, so this is the momentum of the bullet. This guy was at rest. Once the bullet embeds, that will be the velocity of the dummy. Okay, exactly like that. If a beam of light comes and hits this guy, if this absorbs it, the momentum transferred to this is that. It turns out if the beam of light hits it and gets reflected, then the momentum transferred is twice that. Okay, so if we have this device, we'll shine the same beam of light, or we'll keep it in sunlight, or we'll shine a laser beam on this device. What will happen? The momentum transferred to this guy is twice as big as this, so it will spin like that. Okay, so this device can demonstrate the momenta carried by light. Okay. I'll show you numbers in a second. Okay. All right. Momentum transfer, when you transfer momentum to an object, you're exerting a force. Okay. Remember, force is dP by dt. This is Newton's second law. Okay. The rate at which you transfer momentum is the force you've applied. Okay. So force is dP by dt. Force over area is pressure. So dP by dt over area is the pressure exerted by light on this object. Okay. And and momentum is energy divided by C. Momentum is energy divided by C for a light. Okay, so dP by dt is du by dt divided by C. Okay, and du by dt divided by area. This guy is S. That's the Poynting vector. Okay, so this is the rate at which energy is energy is being transferred. Per unit area is the Poynting vector. That's the intensity of the beam. So the pressure exerted by a beam of light, what this formula is saying is the pressure exerted by a beam of light is the intensity of the beam divided by C. This is for an absorbing surface. Okay. For a reflecting surface, this is for an absorbing surface. For a reflecting surface, the pressure is 2 times S over C, okay, or 2 times I over C. And this is I over C, I being the intensity of the beam. Okay, this stuff is real. So for instance, here is a comet. Okay. Do you guys know what a comet is?
Big ball of ice.
It's a big ball of ice and dirt. Okay. So bit of rock and big ball of ice and dust. And when the comet gets close to the sun, a bunch of stuff evaporates, okay? And the sun, what is the sun doing? The sun is emitting a bunch of photons, and charged particles also escape from the sun. Okay, so light and charged particles. This is called solar wind. The charged particles are called solar wind. And photons are just neutral particles. Okay, they're electromagnetic waves. So when the sun emits this, okay, in the comet, this stuff evaporates and some of the stuff ionizes. Okay, so when the comet gets close to the sun, so now this thing, the comet has become a bunch of particles, and some of the gas gets ionized as well. Okay, so the sun, which is emitting photons and charged particles. Okay, the sun is emitting charged particles and photons. The charged particles emitted by the sun, the solar wind repels these charged particles. And the photons only blow the neutral particles. So this comet has two tails. The neutral particles are blown by the photons, and the charged ionized gas is blown by the solar wind. Okay. Maybe I'll draw another diagram here. All right, so here's the sun emitting photons and charged particles. Here's the comet, and the comet, this is neutral particles and ionized gas. And the solar wind blows the ionized particles like that. And the photons blow just the neutral particles. So the comet will have two tails. Okay? And that's what this diagram is showing you. Okay, so there's the comet, and the sun is somewhere here. There's the ionized gas, and there's the neutral dust particles. Okay, so this is actually showing you. So this is demonstrating the photons, light exerting pressure, which is blowing these dust particles. And here's the solar sails. Okay, so the Japanese sent out a sail like this. Okay. What is the advantage of this guy? Why would you want to do that?
You don't have to power it, it's just powered by the sun.
That's right. Okay, so the sunshine bouncing off is giving the solar sail a push. Okay, and so you don't have to use rocket fuel. And how long will this thing work? When will this thing work?
Whenever there's any light.
And so this works if you're close to the sun. Okay. If you're far away from the solar system, for instance, if you're not close to a star, then this will stop working. But as long as you're close to the sun, it works 24/7. And for free. Okay. All right, so let's look at this. So the Japanese sent out launched a solar sail in 2010. Let's look at the numbers. Here's a Wikipedia page. Okay, bless you. So the Japanese sent out a solar sail launched in 2010. The total force exerted on a 800 meters by 800 meter sail. So for instance, 800 meters is from our main entrance on our campus to Krispy Kreme's on Nova Road. That's roughly 800 meters. So imagine a square that big. is about 5 newtons, 1 pound. That's the force exerted by the light. Well, it's a small force, but you know, it's how long is it being exerted? All the time, 24/7. You know? So little drops of water and little grains of sand make the mighty ocean. And so even though the force is small, it's being exerted 24/7. Okay, and can be useful. All right, now we're just going to mention all the different kinds of electromagnetic waves. So, all right, so here's a few formulae that you need to remember. C, what is C? The speed of light, the speed of the electromagnetic wave, that's the frequency, that's the wavelength. What is this formula? That's the energy of the photon. H is the Planck's constant. F is the frequency of that light. Okay, and you see, as frequency increases, the energy increases. Okay, but as frequency increases, since the wave, this is the speed of light. As frequency increases, wavelength decreases. All right, so here's various electromagnetic waves arranged via wavelength. So longer the wavelengths, less the energy of the electromagnetic wave, less the energy of the photon. Okay, so here are shorter wavelengths. All these guys are electromagnetic waves. They all travel at the same speed in vacuum, at the speed of light. Okay, and these are higher energy. What are these guys? Visible light. And what does that mean?
It means our eyes can detect.
That's right. Okay, so you are born with a device that will convert electromagnetic waves into a nerve impulse. And that device of yours works only for this window, small window. Yep. Yep.
So, in terms of the electromagnetic waves that we've detected, the shortest wavelength has been 10 to the negative 12 meters.
Oh, no, we've detected higher, shorter wavelengths. Yep. This is, yeah. Okay. Now here's another interesting thing. Okay. You guys remember, if you want to see let's say you want to see this object. Okay. How do you see this object? How do you see any object?
You bounce electromagnetic waves off
Okay, so a signal has to bounce off there. Not necessarily an electromagnetic wave. You can see stuff with ultrasound, sound waves, any wave. Okay. Now, for you to be able to see this, so if you send a signal that big, okay, whose wavelength is that big, you won't be able to see this guy. Okay, to be able to see this guy, the wavelength of your signal needs to be smaller than that wavelength, that device. Okay. All right. So what this means is, so here's a wavelength, kilometer wavelength. You can't use this wave to see this guy. Okay. To see this guy, you can use any of these waves. You can't use any of these waves. Okay. Do you guys understand that? All right. So radio waves, they have, so their wavelengths is roughly the size of, well, 1,000 meters and so on. That's what this thing is showing. So for instance, if you want to look at nuclei, you would need gamma rays. Okay. If you wanted to look at atoms, you would need X-rays. You couldn't see an atom using a UV light. Okay. You certainly can't see an atom using visible light. Okay. So that's where X-ray crystallography comes. When you want to study crystal structures, you have to use X-rays. Okay. So the probe you use has to be roughly the size of the object that you're seeing, or smaller. Okay. So if the wavelength is smaller, you can see that object. What this is showing you is, okay, so the temperature of an object will emit. So if something is, what is the surface temperature of the sun?
10,000 Kelvin.
6,000 Kelvin. Okay, so roughly, okay, so that tells you if the object's temperature is that'll tell you the wavelength it'll emit, peak emission. Okay, so if blue stars are much hotter stars. Okay. All right. Again, the detector, you have an electromagnetic detector. Your eyes are sensitive to that narrow band. Okay. So there's the wavelength. You're sensitive from 400 to 700 nanometers. Okay. By the way, so you see about your sensor can see about 7 million shades. Okay. What can your computer render? So you can see about 7 million shades on the average. Your computer, I believe, can render about 16 million shades. Okay. Here's the relative sensitivity. Okay, so when a photon falls on your eyes, what does it do? It generates a nerve impulse. Okay. So let's say if what this is showing you is if one photon of this color falls on your eye and it generates a nerve impulse, maybe 10 photons of this guy has to fall before they generate that same impulse intensity. Okay, so it's showing the relative sensitivity. Yeah. The human eye is most sensitive to yellow-green color, and that's why tennis balls are colored then. What is a dipole?
A partial charge on a molecule.
No.
Well, a dispersion of electrons around something more electronegative.
Be more precise. What is a dipole?
A pole.
No. So here's a dipole. Okay, equal and opposite charges separated by a distance. Okay, so if you take, so for instance, if you take a methane molecule, okay, so a methane molecule is pyramid shaped. All right, well, okay, but the center of its positive charge and center of its negative charge are exactly on top of each other. Its dipole moment, the dipole moment is denoted by P, and it's this charge times the distance, Q times D. The dipole moment for the methane molecule is 0, exactly 0. Do you guys remember any molecule that has a dipole moment?
Water.
Water. The Mickey Mouse molecule, this guy has a dipole moment. Okay, so where's the dipole moment? Okay, the water molecule is greedy for the electrons, so here is the center of the negative charge, and here is the positive charge. Okay, so it has a dipole moment, and the dipole moment is that. Okay, let's say here's a water molecule with its dipole moment like this. Okay. Now, if I put an electric field like that, what happens to the dipole moment? So the dipole moment is, there is the positive charge, there is the negative charge. The electric field will exert a force on the positive charge in this direction and on the negative charge in this direction. So what the electric field does is it turns the dipole moment in that direction. So an electric field will turn the dipole moment like that. Okay, when it turns like this, now what I'll do is, I want to mess with it. I'll flip the electric field. So now what happens? This guy was turning like this. When you flip the electric field, it'll turn back like that. Okay, I'm going to be mean. I'm going to change the electric field 5 billion times a second. Like that, that. So what I'm doing is I'm grabbing hold of a water molecule and jiggling it back and forth like that. 5 billion times a second. How can I flip this electric field like that? An electromagnetic field does that. An electromagnetic wave can do that of the frequency 5 billion hertz. This is a microwave. That's what happens in a microwave. So this electromagnetic wave grabs hold of the water molecule in your food and jiggles it back and forth 5 billion times a second. And that's how it heats the water molecule. And then that water molecule heats the neighboring molecules. That's how your food gets heated. Okay. So the oscillating electric field in a microwave oven exerts a torque on a water molecule, okay, because of their dipole moment. This torque reverses direction 5 billion times per second. So let's say I put a whole bunch of methane. I put a methane gas in your microwave and turn on your microwave. Will the methane heat up? No. If I put a whole bunch of steam in a microwave, will the steam heat up? Yep. All right. So only molecules with dipole moments can be heated in your microwave. Okay. All right, guys. I didn't realize there's a couple more slides. Okay. So here's how you produce electromagnetic waves. So here's the device that's pumping energy. Okay. So you set up oscillations that are talking to this, and this dipole antenna will emit electromagnetic radiation. Okay. So this is how an FM station works. Okay. So if you're emitting 100 megahertz signal, okay, so this thing is oscillating 100 megahertz, 100 million times a second, okay, and so is this guy. Okay, so, and here's the dipole antenna. So here's the radiating antenna, okay, and a dipole antenna is made of 2 rods connected to an oscillating source. The length of each rod is equal to 1/4 of the wavelength to be emitted. So if you want to emit a wavelength lambda, the length of this rod is lambda by 4. Okay, so that's the optimal length for emission. The magnetic field lines are concentric circles around the antenna. So here the magnetic field line is coming out, going into the paper. It's concentric circles. Okay. Okay, and so here's a dipole antenna. The intensity is maximum. There's the pointing vector. The intensity is maximum in this direction, and the intensity is 0 along the dipole antenna. So if this was a radio station, if you hover around the radio station, you don't get any signal. Okay, signal is maximum at this ground level. Okay, so the intensity varies like so, and it's given by sine squared theta, where theta is this angle divided by r squared. Okay. Oh, what is AM and FM radio? What does AM and FM stand for? Anybody? AM stands for amplitude modulation. FM stands for frequency modulation. Okay, so let's see what those mean. Okay. So back in your grandparents' era, we didn't have frequency modulation. Okay. So back in the old days, it was only AM radio, and you would have a lot of noise. So here's what was going on. Okay. So, so here's AM radio. This is 1,000,000 hertz. That's the frequency of the carrier signal. What is the sound frequency that you can hear? What is the sound frequency? 20 hertz to 20,000 hertz. Okay? So let's say 1,000 hertz is what we're just picking a sweet spot. Okay, so AM radio, this is 1,000,000 hertz. Okay, so what we're going to do is we are going to put this signal, 1,000 hertz signal, is going to ride on this carrier signal. Okay, so here is the sound wave, the message, here is the sound wave, that's about 1,000 hertz. And there's the carrier signal. The green is that signal. Okay, so you combine this wave with that wave, and now that's the signal being broadcast. The sum of this and that green wave is that red wave. And you see, the amplitude is modulated on that signal. And this signal is broadcast, and your radio catches it, and then it separates the two signals. That's how message is carried. Okay. Now this guy is subject to, so this guy, your radio will pick up noise as well, and so you get a noisy broadcast. So the FM people, what they did was, to fix that problem, they did the following. So here's the message again. And again, the message is 100,000 hertz. And FM radio is, there's FM radio. It's 100 million hertz. The carrier signal is 100 million hertz. Okay. Now what they're going to do is, they're going to, have you guys done Fourier transform in your classes yet? I don't know where you'll do it, but you'll do it eventually. So a Fourier transform is, okay, so let's say here's a signal, and here's a time signal. Yeah. So here's a time signal. There's your message, okay? And if it's a repeating message, so let's say, well, we'll just say that Fourier transform is, what you do is, so if it's a repeating signal, what it's doing is, see, this is the Fourier transform. What this tells you is how much of this frequency is contained in this signal. Okay, so it's telling you what is the frequency mixture of that signal. Okay, so you take the Fourier transform of that and then change the frequency of your carrier signal. The green signal is the carrier signal, and you see you're changing the frequency of that, and the red wave is the modified signal. Its frequency is modified. You modify its frequency, and that's the FM radio. Yeah. And so the amplitude is constant, except that the frequency is changing. And this guy, noise doesn't interfere with it. So randomly created noise can't interfere with the frequency modulation. The advantage of this guy is this guy can travel a long ways. This guy only travels a short way. So this signal can only be line of sight, in the sense that it can only be, you can have 100 miles away FM station. You can catch a radio signal, AM modulated radio signal from New York. It'll bounce off the ionosphere. Okay. So this is noisy, but it can travel long ways. This is not noisy. Do you have shortwave radio? No, all FM radio? Okay.
My car can do AM radio.
Your car can do AM radio?
Yeah.
Okay.
Yeah, it turns on, and it's very, very noisy.
Right. But you can catch a Chicago station with it. Right. You can't catch a Chicago station with the FM radio. Yeah. So again,
What's the range of FM radio usually?
well, so I mean, the FM stations that you get are from about 95 megahertz to 110 megahertz. So very short. Yeah. All right, guys. So that finishes this chapter.